Okay, Chem 1110 students, we are going to be looking at gas laws here in Chapter 11. Gases are extremely important. Many reactions occur in the gas phase, and of course, gas surrounds us all the time in our atmosphere. So it is something that's important to chemistry. Gases differ from solids and liquids in several ways. For one thing, a gas will take both the shape and the volume of its container, and gases are compressible. As we know, you can push a cylinder and reduce its size even though there's gas in it. The densities of gases are much smaller than those of liquids, which makes them compressible, whereas liquids are not. And their density depends a lot on the temperature and the pressure. The other thing about gases is they form homogeneous mixtures because they're always moving around as the gas in our atmosphere is. And that is based on the kinetic molecular theory, or maybe I should say it led to the kinetic molecular theory. And it says that that molecular nature of gases is responsible for the properties, the macroscopic properties that we can observe. So kinetic molecular theory is something that is saying we can explain things by knowing that molecules are always moving. And there's some basic assumptions about gases. Gases are composed of particles that are very far apart, and the volume of each particle is negligible. Gases are always moving, as I mentioned before. They move in straight line paths until they collide, and they have perfectly elastic collisions. Gas molecules experience no attractive or repulsive forces with one another because they're moving all the time, and they're moving so fast. And the average kinetic energy of a gas molecule is proportional to its absolute temperature. So we are saying that when you heat a gas up, it's going to move faster and dissipate. So we know that gases are compressible because the molecules in the gas phase are very far apart. That was our first assumption. And the pressure is a result of collisions of gas molecules with the wall of whatever kind of container they're in. If you have a balloon, it stays inflated because you put gas in there that is moving around and pushing against the wall of that balloon, consistently keeping its shape. If you decrease volume, you squeeze that rubber or that balloon down, it's going to increase the frequency of the collisions, and then the pressure increases because remember the pressure is due to the collisions. And so we just have a little picture here. If you had a piston, your molecules in the left picture are fairly far apart, they're all moving, you see you have a fairly low pressure. When you push that cylinder down, the molecules are much closer together. They're going to hit that cylinder much more frequently, and the pressure is higher. If you heat a sample of gas, it increases its average kinetic energy because kinetic energy is 1/2 mv squared, and you're going to change that velocity. So gas molecules move faster when they are heated up. Faster molecules collide more frequently and at a greater speed, so therefore the pressure is going to increase if you heat a sample up. So now we're going to look at two behaviors of gases due to their movement. One is diffusion, and diffusion is the mixing of gases just from their random motion. And so if you had two containers connected by a stopcock, one has the yellow gas and the other has the kind of fuchsia color, and if you open that stopcock, just the sheer fact that they're moving around will mix them into a homogeneous mixture. Another kind of movement, though, is effusion, and this is if you have all of your gas on, for instance, like the left-hand side of this box, and you do have an opening into a vacuum. So there must have been a little slider in there such that you could pull a vacuum. And when you pull that slider out of the way, because the gas molecules are moving and there is no resistance from the side with the vacuum, they effuse into that side. All right, so Graham's law, which talks about effusion and diffusion, says that that rate of effusion or diffusion is inversely proportional to the square root of its molar mass. So in other words, larger molecules are going to diffuse or effuse slower. So the rate is proportional to 1 over m, and that it's a script m, stands for molar mass. And so here is a problem which we will go through in class, where you can actually look at or determine the identity of a diatomic gas by knowing how fast it moves compared to CO2. All right, now we're going to look at gas pressure. Pressure is defined as force applied per unit area. So pressure is force divided by area. The SI unit for force is the Newton, and the SI unit for pressure is the Pascal, which is defined as 1 Newton per square meter. And there's a whole lot of units for pressure. Generally in this country use the standard atmosphere, which is over 101,000 pascals. We talk about millimeters of mercury in the lab, and that comes from using a barometer which was filled with mercury. You can see a millimeter of mercury is still much bigger than a pascal, 133 times. A torr is equal to a millimeter of mercury. And we often talk in weather, they talk about torr, or they talk about bars or millibars. And a bar is on the same order of magnitude as an atmosphere, but it is a decimal multiple. You can see 10 to the 5th pascals. So an important relationship that was discovered by Boyle is a volume pressure relationship between gases, and it says that the pressure of a fixed amount of gas at a constant temperature is inversely proportional to the volume of that gas. So we would write this as volume is inversely proportional to P. A little bit more useful formula is when you make this an equality. So P1 V1 equals P2 V2, and we will use that relationship quite often. But here is just an example of what it means. So you start at 760 millimeters of mercury, you double that pressure, your volume drops in half. And then if you actually go to 3 times the original pressure, your volume is 1/3 of what it was. And here we have a problem. We will do a couple problems we will do later. Another gas law that came along about the same time as Boyle's law was Charles' law. It's also known as Gay-Lussac's, but somehow Charles got top billing. And this refers to the volume and the temperature of a gas. And so once again, still kinetic molecular theory. And basically it says if you have a balloon at quote unquote a high temperature, maybe it's room temperature, and then you dramatically lower it by pouring liquid helium on it, you see that the volume decreases significantly. And it just says that the volume of gas is directly proportional to its temperature. That's an absolute temperature, so it's Kelvin. So the volume is proportional to the temperature, or V1 over T1 is equal to V2 over T2 as long as your pressure is constant. So remember, from Boyle's law, we were looking at an inverse relationship. So it was P1 times V1 equals P2 V2. In this case, because they're directly proportional, if the volume goes up, the temperature has to go up, or vice versa. And so here's a situation where you could actually plot that relationship, and you'll get a straight line with a positive slope. And we've got a couple of gas law problems there. And the last one we're going to look at is Avogadro's volume relationship. It's amount and volume. And it states that the volume of a gas is directly proportional to the number of moles in the sample, which would seem reasonable for Avogadro. So the volume is proportional to your number of moles, or once again, make it an equality so it's more useful. V1 over N1 equals V2 over N2. And this is just a way you could look at it with a chemical reaction. And that's it for this portion of chapter 11. You can move on to the second part.